Now let's look at an example. This is 16.2, looking at study times. Suppose that the distribution of weekly studying times among the population of all Cal Poly students has a mean of 20 hours and a standard deviation of 8 hours. Are the numbers 20 and 8 parameters or statistics, and what symbols should you use for them? Well, we're told right away that these are based on among the population of all Cal Poly students. So we're looking at the population numbers. So these are parameters. We should use mu for the center of 20 and sigma for 8. Suppose that you select a simple random sample of 75 Cal Poly students and calculate this sample mean studying time. Describe what the central limit theorem says about how this sample mean would vary from sample to sample and include a well-labeled sketch to illustrate this sampling distribution. Well, going back to that central limit theorem, let's think about the validity conditions first. Are there more than, if we look at 75, are there more than 750 plus students at Cal Poly? And the answer is yes. So the 10% criteria is met, and the sample size, we're not told that it's extremely skewed. I don't know if it's extremely skewed, but we're going to say n is greater than 40 is sufficient. So we've checked the conditions. We know that n equals 75, which is greater than 40, and the 10% condition is met. Therefore, we know that it's going to be bell-shaped based on its central limit theorem. It's going to be bell-shaped. In other words, look like a normal distribution. The center will be at 20. Now the mean is 20. The standard deviation, remember, of these these are all the sample means here, is going to be 8 divided by the square root of n, which is 0.924. So this variability is scaled by our sample size. Cool. Part C. In a random sample of 75 students, determine the approximate probability that the sample mean, the average, study time would be more than 21.5 hours. The very first thing I do, to be honest with you, is I don't even more than, I do a really quick and dirty sketch, okay? Before I do anything else. And that way I know what area I'm looking for under the curve. Because remember, the whole thing with p-value is finding that area under the curve to see how extreme or more extreme the 21.5 hours or more is, how unusual it is. What do we know? Well, we know that X bar, in this case, is going to be 21.5. We know that the mu is 20, and we have that standard deviation of those X bars. We calculated above being 0.924. So Z in this case, remember, is our sample minus the center, that population parameter, over that standard deviation. So to calculate it out, there we go, we get it set up and we get 1.62. Now we're going to go to the table. Remember that Z table, that standard normal table, is going to give us this area here. And the area it gives us is 0.9474. So that probability, in other words, the p-value, is going to be 1 minus 0.9474, which gives us 0.0526. So about 5.26% chance the study time is 21.5 hours or more. In a random sample of 75 students, what's the probability that the average study time is between 18.5 and 21.5 hours? So this is just more practice. There's two ways to approach this. You can either take the p-value for the 21.5 and then subtract out, using that z-score, the area under for 18.5, and if you take that away, you would be left with the area in between the two. That's one way to do it. The other way to do it is to use what we have in C and realize that this is symmetric around that this is 1.5, that 21.5 is 1.5 more, and 18.5 is 1.5 less. So we could then use the properties of symmetry there. But honestly, I would probably do it old school. I would just say I would get the z-score for this, and then find the p-value, the z-score for this, and then get the p-value, and then take the difference. We did that a lot early in the quarter, so I'm going to tell you that the answer is 0.948. And please make sure you practice so that you can get that. If you're struggling at all, please come to office hours. So what does that tell us? So about 89.5% have an average study time between 18.5 and 21.5 hours. Now, are the answers B through D valid even if the distribution of study times in the population is skewed? Explain. It is possible that the distribution is skewed. It didn't say anything in the description about it being symmetric bell-shaped, but the central limit theorem says we can still use here as n is greater than 40. Now, if we had an inkling that it was very skewed, we'd want to use n greater than 100, but there's no indication at this point that it would be a very skewed distribution. For you to use n greater than 100, I would make it clear that the distribution is very skewed. So based on that central limit theorem for part E, we can still use as n is greater than 40. Would these probabilities in C and D increase, decrease, or stay the same if the sample size was larger? So you need to think about that carefully. What happens as n goes up? So our sample size goes up. What happens to our variability? Well, hopefully you think, well, my variability goes down. So this is for part C. My variability goes down. So what's going to happen to my tail here? Standard deviation gets smaller. My tails are going to get smaller. Okay. So do I expect that probability to increase or decrease? And I expect it to decrease. In the same vein here, looking at part D, remember the tails are going to get smaller. So what's going to be left in here in the middle is going to be bigger. So this is going to be larger. So the probability would go up for part D. If you're not seeing this, you can, of course, take as n goes up, probability goes down because the tails get smaller. Larger samples look more like the population average. You can reason this out without calculation, but as I was starting to say, if you're not seeing it, what I suggest doing is trying it, but with a population of, let's say, n, or a sample, excuse me, sample size of n equals 200. And you should be able to, it'll show you then. You should be pretty clear. For the probability in C to be less than 2% or 0.02, how many students have to be sampled? So this is a little bit different. So we're going to redraw what we had in part C. Our center is at 20. What we want under the curve, though, is 0.02 here. And we don't want to know what the sample size is. So the first thing we're going to need is the z-score. The z-score is going to be related to that 0.98. So remember, it's the area under the curve here. So that we end up with 0.02 in this table. So we're looking at the inside of the table to go out. Once again, this is a review from early in the quarter. So my z-score has to be 2.05. I then am going to say, okay, I'm going to solve the rest of it, but I don't know what my n is. Okay. Now, use algebra base and you get n equals 119.54. Even if it was 119.1, I would still round up to be more conservative. So having an extra one is better than having one less in terms of taking a sample. Now, big question is, does the given information allow you to determine the probability that an individual student studies for more than 21.5 hours per week? And it's tempting to say, yeah, it does. I can look at the individual students and say something, but the answer is actually no. We have to know the distribution of the population, and we don't have that. All right. We aren't told the shape of the population distribution, so we just don't have enough information. Remember, we're using that central limit theorem for samples. Okay. It gives us, we look at that normal distribution of sample means. We're not looking at what happens with individual students in the population.